Hello everyone, this is Mohammed Yaqub. I hope everybody's having a very nice weekend, and it's time again for another STM32 tutorial. And today's tutorial is going to be a very interesting one. So today I'm going to show you how to use CAN bus. And I believe many people have written down in the comments of my videos that they want to see CAN bus tutorial. So here it is. Let me give you a very brief introduction about CAN bus before we get started. So CAN bus protocol looks like this. You have an ID, so that's the CAN bus device ID, and you have the data length and the data that you want to send. And you can send up to 8 bytes, I believe, with CAN bus, and then comes a CRC field and so on. But with the STM32 CAN peripheral, you don't have to do any of this protocol by yourself. All you need is to give the STM what your ID is and what the control bytes and the data, and it will do the rest. It will calculate the CRC and it will manage the transmission and collision and all of that details. All right, and what you need for today's demo, I'm going to communicate between two STM boards to send and receive data over between the two boards. And what you would need, you need two CAN bus transceivers. I'm using the CubeMX 1051 module. But I believe you can use any CAN bus module as long as it works the same. So for the connections, you need to connect the CAN TX of the STM to the CTX of the module, and similarly for the RX, and same for the other board, TX to TX and RX to RX. And most importantly, you need to connect VCC to 5 volt. I think if you connected it to 3 volt, I don't think it will work. It needs a higher voltage. Alright, and you need to connect the CAN high and CAN low all together with a twisted pair preferably, but I think for short distances it would work with a normal jumper wire, just like what I have in here. And my demo today would be to synchronize two LEDs with the two STM boards. So that's basically, it's actually one of the ST examples that they provide, and I'm going to show you how to make it from scratch. So the final working application will look something like this in the video, where I have two STM board, and when I press the button here, the two LEDs synchronize together. And same thing when I do it with the other board, the first board get synchronized too, and it's all with CAN bus. Okay, so let's get started and set up a project in CubeMX. And on CubeMX, first click on New Project, and then select the right board. So I'll go to Board Selector, and it's the Discovery of 4, and it's the 4 Discovery that I'm using. I'm using 2 of them. Okay, and on the pinout, as usual, I'm going to clear everything out and then set it up from scratch myself. So first thing I'll do is I'll enable my LEDs because I need them in my application. So PD 12, 13, and 14 and 15 for my LEDs. And I'll enable the push button because it's part of the demo too. And now I can enable the CAN bus peripheral. So on the peripherals, go to CAN 1, that's the master CAN bus, and enable it. And this will get mapped out to PA11 and PA12. And I don't want to use PA11 and 12 because I think those are part of the USB on the go. And the circuit gets a little bit messy. So I want to map them out to a different pin. I want to map them out to BB8 and BB9. That's where my wiring is done on. So what you need to do is click on Control on your keyboard, Control and then left click of the mouse, and it will show you what are the alternatives. So drag it over to BB8. Okay, and same thing for the TX, Control on your keyboard, and it will show you what are the alternatives. And I want to connect it to BB9. Okay, that's as simple as this. And if you don't know how to do this, you can do it differently. So you can just go straight to BB8 and enable CAN RX, and it will automatically come here. The same thing for the TX. Okay, that's very simple. Next thing I want to enable is that I want to enable the external oscillator. It's much more stable. So go to high speed clock and select the ceramic resonator. And now let's go to the clock configuration window. I will select the external oscillator, and I'll set the frequency to 84 megahertz, and it will do the rest automatically. Next, go to the configuration tab, and I need to configure my CAN bus. So on parameter setting, I'll set the time quanta bit segment 1 to 4 and segment 2 to 2. So these timings are described in details in the reference manual of the MCU, and some of them are application dependent, but for application 4 and 2 will do the job. And then I'll leave everything else as default. The operating mode needs to be normal, just like what it is. And the other modes are for testing. So loop back, silent are for testing, not for normal operating. Okay, and then let's go to the interrupts, and I need to enable the RX0 interrupt. And that's it. Click OK, and we are now ready to generate the code. So click on generate source code icon, and I'll call the project CAN video, perhaps, or CAN tutorial. And I'll store it at this location and select your correct IDE. I'm using MDK ARM v5. And one more thing, I want to use a different firmware package, but you don't have to do this. But I like to use version 1.18. 1.18. I think it's one of the most stable firmware for CAN bus. But you don't have to do this. I've got all of them installed in my repository, so I'll select 1.18, and most importantly, it has to be the 4, and click OK. But as I said, you don't have to do this yourself. And while this is loading, for any of my professional business contacts, you can get in touch with me through mutexembedded.com. All right. And now let's just wait for this to finish generating the source code. All right, code is generated successfully. Click on Open Project, and this will take you to your IDE. Okay, and on Keil, the first thing we'll do is that we'll open the main, and we'll do basic initialization to the TX and RX message. So I've got this in my steps of making this demo. So after setting up CubeMX, we need to declare TX and RX message type diffs and set them in the initializer of the CAN bus. So it's just something like this. So you go to private variable section, and I'm going to define two variables. This is TX and RX message structure, perhaps structure or type diff. It's actually a structure type diff type. Static CAN RX message type diff, and automatically came out. And I'll call it my RX message, and same thing for the TX. So CAN TX message type diff, and I'll call it my TX message. This is where all the RX and TX message data are stored. So things like I show you on the CAN bus frame. So this variable, when you navigate to the definition of it, but I don't think it will go because code is not compiled yet. Let me leave it compiling while I'm doing the tutorial. So this variable acts as a structure, and it stores all of these variables. So the ID and the type of the ID, whether a standard or extended, and then the data length and the data bytes and things like that. So that's what it is for. And after defining it in here, we need to initialize it as part of the CAN bus initialization. So scroll down till you find CAN bus initialize, this one, and you need to add it as part of the field here. So hcan1 dot ptx. Oh, it's not coming out. So let me just wait for it to finish compiling, and then we'll carry on with writing this code. All right, finish compiling. So what we need to do is, as part of the initialize, we need to write ptx and set the tx message here. So we define a variable for the tx message that will store all the parameters. So let me copy it to here as a pointer. So you need to put the ampersand sign. And similarly, we need to do the same for the RX, because this will store all the TX and RX parameter in this variable. Okay, so and if I go to the definition of those, you will see what parameter those things hold. So go to definition. You see what this holds? It holds the standard ID, whether it's and the ID type, data length, and data, just like what I show you in here. Okay, so that's what this variable is for. Okay, having done this, we're done with the initialization function. Next step is to do the CAN filter config function. So that's to configure the CAN bus filter. If you want to filter out certain IDs, it's necessary. So I'll create a function for it. Function prototype will look perhaps something like this: void my CAN filter config. Actually, I don't need the my CAN here. Okay, and this doesn't take any parameters, and it will initialize and it will configure the CAN filter. And I'll do the function definition in begin number 4 as usual. And the function definition looks something like this. You need to define a CAN filter config type div that will store all the filter configurations, so that then you can pass it to the config filter function. Okay, so we need to define a CAN filter config control space if you want to see the options. So CAN filter config type div is the one we're looking for, and I'll call it CAN or just filter config. And then what you need to do is that you need to set all of those fields. So bank number, filter activation, filter FIFO assignment, filter ID high, and filter ID low, and all of them. So I'm going to go over all of them now first, and then I'll write their parameters. Then filter mask ID low, this is for the extended only, and then the mode, and hopefully finally, not yet, filter number, sorry, and finally filter scale. First, bank number is 14, and then filter activation is well, you need to enable the filter, so set this to enable, and then filter FIFO assignment to, I think, 0, something like that. Yeah, we're using FIFO 0 or things like that. And then filter ID high, I'll set all the filter parameter to 0, because we're not, I'll show you later on how to enable filter. Now I'll keep filter disabled, so I want to accept all CAN traffic. I don't want to filter out anything for now. I'll show you later on how to filter out certain IDs, or perhaps how to allow certain ID and filter the rest. And the filter mode is ID mask. So there is something called ID list and ID mask, and details are described in one of the ST forums if you want to know more details about it. So this is CAN filter mode ID mask. Okay, that's the one. And then filter number is 0. Okay, and then filter scale is 32-bit, because there is 16-bit and 32-bit for the filter scale, and there is a purpose behind it. And then finally, I need to call in my hull CAN config filter function. So hull CAN filter config, or config filter function rather. And this function takes 2 parameters. It takes the CAN handle, and it takes the filter config type div. So it CAN1 as a pointer, and then the filter config as a pointer too. Alright, that's it. And I can do the error check as well. If this is not equal to OK, then I can do the error, but I think this one will always work, I believe. So, alright. So this is the CAN filter config, and what we need to do is that we need to call it at the start of the main to implement those filter configurations. So filter config, we need to call it in here. All right, next thing is that I'll define the LED switch function. As you saw in the demo, when I click the button of the first STM board and I keep it there, it will switch between LEDs. And that's what this function is for. You give it a number from 1 to 4 and it will switch between LEDs. And this is a very straightforward function, so I don't want to spend a lot of time on it. I'll just copy and paste it. And I'll put this txt file down in the description of the video as well if you want to copy over the steps. So I'll copy it. It's a LED switch. I first need to define the functional prototype in here. So this is LED switch. And then I need to do the function definition in bigger number 4. So just copy it over. And in bigger number 4, this is my LED switch function. Very straightforward. All it's doing is switching off all the LEDs at the beginning, and then based on the number, it will turn the right LED on. Okay. And then next, we need to do the main initialize function. So I already did that for the CAN filter. So you call the filter config at the beginning of the main to implement the filter configuration, and then we need to start the CAN receive interrupt before we do anything, because this will just start listening for any CAN traffic, and when anything arrived, it will jump into the CAN receive callback that I will show you in a moment. So let's first start CAN IT receive, and the function looks like this. So hull CAN receive IT, do it in here. And this is basically start listening for CAN traffic with interrupt. So hull CAN receive as interrupt, and the function takes two parameters. It takes the hull, it takes the CAN handle, a pointer to that, and it takes the CAN utility, what FIFO you want to use. We've got two FIFOs. You can choose any of them. I'll go with FIFO 0. But I would have to go with FIFO0 because I have enabled RX0 interrupt, if you have noticed, not RX1. So that's what I need to do here. All right. And next, I need to do the transmission CAN parameters. Before I do that, let me define two variables for the CAN bus IDs. As I show you, you need to define the CAN ID for the device as part of the bucket. And because I've got two STM boards, so I need to have two IDs for my own board and for the remote board. And I can keep them the same as well. So let me define two variables for them. My own and remote IDs. Unsigned integer 8, or sorry, rather 16. I'll call it my own ID, and that's equal to 0x123, for example, and then the remote ID for the other board. For simplicity, I'll set it to the same for now, so that I can flash the same code into both boards and it will work. And I'll also demonstrate to you the case where we have different IDs. And all you have to do for different IDs is that when you flash it into the first board, flash it with this order of IDs. And when you flash it into the second board, just to swap the IDs, because now the second one will be the on and the first one will be the remote, and so on. I hope you got that. So that's it. And then now I need to set the transmission parameters before I transmit any things. So it will be in that begin number 2 again, set transmit parameters. So that will be the CAN bus protocol parameters. And for that, we need to use the CAN handle and go to the PTX message, the one we set at the beginning, as a pointer. So I'll first set the type of the ID. So we are using a standard ID, not the extended. So you need to do this. CAN ID is a standard. And then next parameter is I'll set the standard ID itself to my own because I'm transmitting. So I'll set the ID to my own ID. And next would be let me set the data, the RTR, so the type of data I'm sending. This is a data because there are two things, either data or command or things like that. But I'm sending data, so just use this one. and then would need to do the data length. Of course, I'm sending 2 bytes, but you can do just 1 byte, or you can do 1 to 8 bytes, I believe, with CAN bus. So data length, I'm sending 2 bytes, 1 for my LED status and 1 just a dummy data that I'm sending over. All right, that's for the transmit parameters. So now I'm ready to transmit data. And for the CAN transmit, we'll do that in my infinite while loop. I'll check the push button status. If the button is pressed, then I will increment the data and send them over with CAN bus. Let me show you how it's done. So in here, if my button is pressed, so if HAL GPIO read bin, reading my push button, which is on port A and pin number 0, and if this one is equal to GPIO pin set, if this is high, then I want to transmit a CAN packet. Okay, and I'll set a short delay at the end of, let's say, 100 milliseconds. Yeah, 200 perhaps. All right, and to transmit, I first wanna I'll have a variable that stores my LED status from 1 to 4. I call it data variable. You can call it anything. So let me it's an unsigned integer 8. I'll call it my LED well, variable, maybe anything. Okay, and I'll initialize it to 0. And what I need to do here is I need to set it to my LED function thing. So LED switch at the beginning, when I press the button, I also want to update my own LEDs and then the remote board LEDs through CAN bus, just like what you saw in the video. So I will increment this parameter. I'll increment it by 1 because it has to be from 1 to 4, not from 0 to 3 or 0 to 4. And the reason, and for that, I will check if this variable is equal to 4, then, well, I don't need the hex anyway. So if this is equal to 4, then I will initialize it back to 0. And what this increment will do is that since I'm initializing it to 0 whenever it gets to 4, and this always increment 1, this one will always be from 1 to 4. If this is confusing, don't worry, just write it down, you'll get it, you'll get what it does. It's very straightforward. All right, and next I can just set the data to be transmitted and transmit them with CAN bus. So it would be hcan1 dot the tx message, and I need to set data 0 to my LED switch. So my LED variable will go on as a first parameter, and the second data, any dummy data, because I'm sending 2 bytes, so I gotta give it another data. So let's say 0x12, for example, anything. And now I'm ready to transmit via CAN bus. So HAL CAN transmit, and this takes the CAN handle, and it takes the just a timeout, so 10 milliseconds or 20 milliseconds, whatever you want, as long as it gets transmitted successfully. And you can also check for an error. If it didn't get through, you can go to the error handler, but I don't want to jump into the error handler. I wanted to try again, so I'll leave it as this. Let's see if there's anything we haven't done. Yep, sure enough, we also need to do the CAN receive callback. So this is the transmit code. Whenever you press a button, it will transmit a CAN packet, but also whenever it receives a packet, it will jump into the interrupt callback. So now let's go ahead together and do the receive callback. For the receive callback, go to Functions tab in Keil and expand the CAN library, and you'll find a receive callback function, receive complete callback, and that's what we need. Let's copy it into our main without the weak object, and that need to go in bigger number 4, the user functions, and in here we will implement the callback routine. So whenever we receive a message, we just want to first double check that the ID is correspond to our expected remote ID, and then we'll go ahead and read the data and update our LED status and start the receive all over again. So here's what you need to do. I first need to check that the received data are actually coming from the specified remote ID, not from other devices on the CAN bus network. So I'll use the HCAN here and the PRX because of the received message. And if the data of 0, sorry, not the data, if the standard ID is equal to our remote ID that we specified, then I will accept the data, update my variable, and then update my LED status. So this is my LED variable, and I'll read whatever data read by the CAN and set it to this variable. So I will do the HCAN PRX and then the data of 0, because this is the data of the LED, and I'll update my LED variable. Just like when we did for the transmit, data of index 0 are the LED, and that will be the same sent by the other board as well, because we're going to flash the same code in both boards. Alright, and now I need to update my LED switch and pass this variable to there. Alright, and then at the end of the callback, I will start listening again for another CAN packet. Okay, and that will be the HAL CAN receive interrupt function that will take similar parameter, the HCAN1 and the CAN 540. Alright, and I believe that's everything for the very basic demo now. Alright, so let's compile the code. Let me just go over it really quickly to make sure nothing is missing. Alright, and what I'll do for simplicity is that I'll set the on and remote addresses the same so that I can flash the same code to both boards. Alright, compile without any errors. Now let's flash it to, let me plug one of my boards and flash the code over to. Now I'll unplug the first one, unplug the second one. There is an easier way, but I like to do it the simplest way. Now flashing the second board. Right, now I'll plug in both of them to power and reset both of them, and let's see if this is working. And sure enough, working exactly as we expected. Now next step is that I said I want to show you how to use the filter thing. So how to filter out IDs. So for the filter function, let me first change the on and remote ID. So my on ID is 1234 and the remote is 123 or 124. You can use any IDs as long as there are 11 bits in width. And now to use the filter, I know that my remote ID is 0x124, and to enable filter, set the ID high to whatever ID you want to filter or you want to allow to pass, and then shift by 5. So 0x124 and then shifted above by 5, because this filter ID high is used by the standard ID and the extended. And for the standard, it's the shifted by 5 spaces in the register. You'll find more details about this in the reference manual of the STM and also in this ST forum. So you'll see a lot more details about why this is the case. I don't want to get into much details of it because it can be very confusing for some. So the most important thing is that you need to set the ID filter. So I want to allow 124 to pass, and in order to make this correct, I need to set the mask ID high to 0xFFE0, and the reason for that is because the ID is 11 bits, so this is 8 bits or a byte, and this is 3 more bits, so 8 plus 3 is 11. And the filter mechanism works in a very simple way. So you do an AND of the mask So if mask and, which is a bit masking operation with the ID that you set here, the filter ID, which is 0x124 in this case. So if this is equal to the ID itself, 0x124, then it will allow it to pass, will allow this packet to pass. For one-to-one packet filter allow, so this mask is always 1, so 0xFFE is just ones, and when you AND ones with anything you will get the same thing. So this will only allow 1, 2, 4. Alright, I hope that makes sense. And it can allow other ones too, I believe. For more details about filter implementation, get to this ST forums. I will include the link down in the description of the video. I don't want to get more details because filters can be very complex. You can implement tons of filter ways, but this is a simple one. So I'm only allowing 1, 2, 4. Let me show you how it works. So I said I want to allow only 1, 2, 4. So I'll flash this to one of my boards because I already flashed one of them. And now this one, the on will be the same, but the remote ID is different. So I believe I need to flash both of them, in fact. So let's compile the code. And flash it to the first STM board. So that will have an on ID this and a remote ID of 0x124. Well, in fact, instead of using 124 in here, let me use the remote ID, because I'll change it for the second board. So this will only accept the remote ID thing. So compile it again and flash it to the first STM board. Now for the second one, plug the second one and unplug the first because Keil can get confused. Need to swap the IDs. Now the remote will be an on and the on will be remote. Compile the code and flash it again. Alright, now I expect it to work exactly the same because the filter will always allow the remote ID to get in. So let's just do a quick test. Reset both boards and run them. And sure enough, it works exactly the same. Now let's do a very basic test to one of the boards. So I know the remote ID of this board, the second one I flashed, was 0x123. Let me change the filter to a different ID. Now it shouldn't work. So if I did it 0x125, for example, now one of the boards will stop working. Right, okay, so I think I have I've confused the boards that I flashed first a second, so let's do that all over again with the filter really quickly. So I'll just reflash both of them the same first. So this one used the remote ID, and then the first board is 124 and then the second board is 123 as a remote. So flashing the first one with this, so I'm just getting back one more step with the filter being the same one, remote ID. I'm not trying anything else with the filter. So I flashed the first one. Now let me flash the second one with the ID swapped. Okay. Now compile the code again and load it. Alright, and now since this is my second one, I want to make this change. So I want to filter out the wrong, I want to allow the wrong ID. Now I don't expect the second one to receive anything, but it will always transmit successfully and get received by the other board. So if I set this one to 225 now and flash it to the second board that I just flashed, I expect one of them to transmit and receive and the other one just to transmit and not receiving successfully. Alright, let's plug it in and do the test. Exactly. One of them transmit and receive and the second one only transmit and doesn't receive successfully because the filter is not working. It's actually blocking the right one. All right, let me see if there's anything I haven't shown. No, that's everything. So basically this brings me to the end of my CAN bus tutorial today. Thanks for watching, and as always, if you found it helpful, don't forget to hit like and subscribe. And for any of my business contacts, you can always get in touch with me through mutexembedded.com. Thanks for watching, and I'll see you in the next video.